Happy morning, students. In this video we will see some important expressions in lesson 2. Okay, first of all, expression for current. We know very well current is a rate of flow of electric charge, so it can be represented as I is equal to Q by T, or we can also written in the form of dQ by dt. Then we know very well current is a scalar quantity. Okay, then next, if suppose a conductor is connected with a cell or potential difference, the free electrons experience an acceleration. Then here we see the acceleration of the electrons when it is subjected to electric field. Can be represented as A vector is equal to minus E vector by M. Here this minus sign represent the direction of the electron flow is in the direction opposite to the direction of the electric field. Okay, first one, second one, then third one. Then drift velocity. Drift velocity state of the electron. Okay, we know the formula for velocity. Velocity vector is equal to acceleration into time. Here the time is mean free time. Okay, then one more form we can write, Vd vector is equal to minus E tau by M E vector. Okay, we also write in terms of mobility, Vd vector is equal to minus mu E vector. Okay, then the term mu is known as mobility. Mobility is a drift velocity acted per unit electric field. Okay, then mu is equal to Vd vector modulus by E vector modulus. The next, current density. Okay, before going to that current density, we see the relation between current and drift velocity. Okay, fifth one, relation between current and drift velocity. We know very well that is an important and valid expression. I is equal to N A V D E. Here this expression indicate the current is directly proportional to drift velocity, that drift velocity is directly proportional to electric field, that electric field is directly proportional to potential difference. Okay, then next, current density. We know current density is a current flowing per unit area. It is represented by the symbol J. J is equal to I by A. Then we can also write this expression as J is equal to N VDE. This expression is only valid when the current passing through a conductor is in perpendicular manner. Then we can write in terms of sigma also. Then J is equal to sigma E. Here this is a microscopic form of Ohm's law. Using this relation we can find the macroscopic form of Ohm's law. Okay, in current density expression, J is equal to sigma E, that sigma represent conductivity. Sigma is equal to N E square tau by M. Here the term N represent number of electron present in per unit volume, E is the charge of the electron, then tau is a mean free time, then M is a mass of the electron. Okay, the reciprocal of this conductivity is known as resistivity. Rho is equal to 1 by sigma. Okay, we can write this one as M by N E square tau. We can also write the resistivity in forms of resistance also, because resistivity is a resistance offered by the conductor when the conductor having unit length and unit area of cross section. So rho is equal to A R by L. here A is the area, then L is the length of the conductor, and R is the resistance of the conductor. Okay, the next, potential difference. We know very well that relation between potential difference and electric field in your first chapter. Here we write potential difference as difference V is equal to E into L. Okay, here L is the length of that conductor. Then our 10th one is Ohm's law. It is also can be stated as macroscopic form of Ohm's law, that is V is equal to IR. Okay, then next we can write resistance of the conductor. Resistance, okay, we can write through this formula also. Resistance R is equal to V by R, or V by I, or resistance R is equal to rho L by E, or R is equal to L by sigma E. Okay, our next one, if resistors are connected in series, we can find the effective resistance also. Okay, for that case, resistors are in series, we can find the effective resistance Rs is equal to R1 plus R2 plus R3. If suppose n resistors of same resistance are in series, we can write the effective resistance Rs is equal to Nr. R1 is equal to R2 is equal to up to Rn. Okay, here in series connection, current flowing through each resistor is constant because there is no accumulation of the charge, and the effective resistance is always greater than the individual resistance. Okay, then resistors are in parallel. Here first of all we consider 1 by Rp, that is equal to 1 by R1 plus 1 by R2 plus 1 by R3. If suppose n resistors of same resistor are connected in parallel, then we can find the effective resistance 1 by Rp is equal to n by R. We need only Rp, so we can write Rp is equal to R by n. Okay, here in a parallel connection, the voltage drop across each resistor will be same. The effective resistance is always less than the individual resistance. Okay, then our next topic, resistivity with temperature dependence. Okay, listen, we know very well the resistivity varies with the temperature. Okay, we can find the resistivity of the material at a particular temperature using the formula rho T is equal to rho naught 1 plus alpha T minus T naught. Okay, using this expression we can find the resistivity of the material at a particular temperature. Okay, here modifying this equation, we get temperature coefficient of resistivity. Temperature coefficient of resistivity. It is a ratio of increase in resistivity to per degree rise in temperature. It is a ratio of increase in resistivity per degree rise in temperature to the resistivity at T0 degree Celsius. Okay, its unit is per degree Celsius. We can write this temperature coefficient of resistance in terms of resistance also. Then alpha is equal to del R by R naught del T. Okay, here also we get a same unit per degree Celsius. Then our next topic is electric power and electric energy. electric power. We know very well power is a rate of doing electric work or the rate at which the electric potential energy is delivered. Then power can be written as du by dt. Okay, rearranging it after some simplification, then power P is equal to VI. Okay, we can write power in other forms also. P is equal to I square R, then P is equal to P square by R by using Ohm's law. Okay, then internal resistance of the cell. We know very well internal resistance is a resistance offered by the electrode and electrolyte of the cell to the flow of charge inside the cell. Okay, internal resistance is always represented by the symbol small r. Here we are finding the internal resistance by the help of voltmeter. For this case we found R is equal to psi minus V by V into capital R. Okay, then next, bridge balance condition. Condition for bridge balance in Wheatstone bridge. Bridge balance. Okay, we know that is P by Q is equal to R by S. The next, using meter bridge we can find the unknown resistance. We can use the formula P is equal to Q L1 by L2. Okay, then comparison of EMF of the two cell using potentiometer. EMFs of two cells using potentiometer. It is represented by the expression psi1 by psi2 is equal to L1 by L2. Then we found the internal resistance of the cell by using potentiometer. By using potentiometer, we know here we get the expression R is equal to R L1 minus L2 by L2. Here in this case, if resistance increases, the internal resistance also increases. Okay, our last one, that is Joule's law of heating. Joule's law of heating. Using this law we can find the heat developed in a conductor when current is flowing through a conductor. Then heat developed in a conductor H is equal to I square RT. Okay, using these relations we can solve the numerical problems. Okay, thank you.